bill.
Okay, this evening I'd like to talk about a low power single polarization 144 megahertz Earth Moon Earth amateur radio station. And I'll be describing the physics, engineering, and some operations. And I thank SciTech Amateur Radio Society for inviting me to do this. So the next slide is the outline of the presentation. Hopefully you can see this little laser pointer here. We're going to talk about QRP EME, that is low power EME. And I'll be defining that more precisely. There's sort of an entry level of power and aperture that you need to be able to work the moon and back. We'll talk about the physics, which includes lunar characteristics, ionospheric propagation, and antenna gain, how the antenna gain is affected by the Earth, for example. Some people refer to that as ground gain. And then I'll talk about the engineering, which includes a description of the radio system that I have, and in particular, a fairly technical description of JT-65B signaling and performance. Then ultimately, under operations, I'll talk about the 6 QSOs that I've successfully worked, model the performance, and then show you the QSL cards. So there's some insights, hopefully there'll be some insights on what you need to operate with a minimal type system. So first of all, I'd like to acknowledge that I didn't do this on my own. Work like this always depends on other people, including obviously Dr. Joe Taylor, who developed, and his associates who developed JT-65B. But also starting here, discussions with Dennis Hall, who lives in Massachusetts, about EME and satellite, and then ultimately talking about some of the physics with Ed Bicknell. Again, discussions via email. And then an interesting thing happened in November of 2018. I went on the air, and I didn't know what the protocols were, what was expected in terms of transmitting. And I'll get into that later. So I just turned on, and I managed to hear the signal from Rhode Island, Bill Corbin, Whiskey 3 Charlie Juliet Kilo. So it was an accidental 2-meter J65B terrestrial link. And it was basically a signal that was going into his side lobes. But I contacted him and I found out that this wasn't an EME connection, but rather what it was. And we set up a meeting with Jim Spears, basically November 1, November Kilo, who's also in Rhode Island. And we talked over EME details, what's expected, the fact that there's a French radar system that's illuminating, and sometimes you can hear it on 2 meters. And then finally, Dr. Marshall Williams, Kilo 5 Quebec Echo, who basically is a very strong proponent of EME, and he operates a big station in Texas. I've never successfully contacted him, and you'll see why the geometry is important in this case. All right, so this project started in 2018. I named it Project Selene, the Greek goddess of the moon. Obviously, Artemis is another goddess reference of the moon. In this case, we're talking QRP, as I mentioned earlier. So this is exactly what I'm talking about. Transmitting a signal out to the moon, having it Doppler shifted. You can see the colors of the lines representing a signal change because the moon is moving. So there's a Doppler shift. And then receiving it, someone else on Earth who has the right equipment and is tuned to the right frequency can receive the signal. And the format that is used is a digital format. A QRP system doesn't have enough signal or enough antenna to be able to communicate either CW, voice, single sideband, anything. It has to be JT-65B because of the incredible signal processing done by that particular format. So I want to define what QRP is. Okay, so generally speaking, most people know QRP means low power operation. But in this case, I'm including the antenna aperture or the gain of the antenna, the product of the two, which generally is spoken of as the effective isotropically radiated power. That is, effectively, if you had a transmitter that was transmitting into 4 pi steradians, that would be the equivalent power. So the antennas act, in a sense, like a lens to focus the energy in one direction. So you can have a 100-watt transmitter and maybe a 20 dB gain antenna and have 40 dB of EIRP, the equivalent of 10,000 watts transmitted in a sphere. So I'm going to demonstrate what EIRP is and what is needed to operate at 2 meters. By the way, I should mention that if you're interested in operating at other frequencies, the numbers will be different for the EIRP. And important for us living in New England, you have to consider the fact that paved pause is a UHF radar on Cape Cod. And generally, you don't operate with these types of systems at UHF. So that's one of the reasons why I chose 2 meters. So now I'm going to talk about key lunar characteristics. Okay, how far away is it? It's about 384,000 meters away, or kilometers rather, away. The lunar diameter is on the order of 2 million meters. So you can calculate the angular subtents. That is, how large is the moon when viewed from the Earth? It's about 1/2 degree. So that gives you an idea of what the pointing constraints are. If you have an antenna that has a 38-degree beam width, you're not going to have to point it very accurately at the moon, as you'll see. So my antenna had a relatively low gain and 38-degree half-width beam width. Another factor, since I've both communications and radar, I prefer to look at this as a radar problem, because we're bouncing a signal off the moon and it's being returned from the moon. There are certain characteristics that are important for radars in this case, and one is the geometric cross-section. How large is the cross-sectional area of the moon if it were projected as a flat disk? If you know what the reflectivity of the moon is, and it's about 7% or so, you can multiply those two together and get, and this is an approximation, get a rough idea of what the radar cross-section is, this rho times A. So it's about 7 times 10 to the 11th square meters. It's easier to express that in decibels, reference to a square meter. So it's 118.45 decibels referred to a square meter. That's really just 10 times the log of this number here. Another characteristic of radar targets is a distribution, an amplitude distribution. And that can be either a Ricean distribution or a Rayleigh distribution. And you'll see measurements have been made on that. So that tells you how frequently the moon presents the mean value of 118 dBSM. And you'll see that in a chart later on. Also, polarization. Linear polarization is not significantly altered by a specular lunar reflection. A specular reflection is a reflection like a reflection off a mirror or a piece of metal. It preserves the linear polarization. If we're working with circular polarization, it'll switch a right-hand circularly polarized wave to a left-hand circularly polarized wave. And then another characteristic is the moon has a fading. That is, the signal strength from the moon can change, and it's not necessarily caused by the ionosphere. That's another factor, but just the motion of the moon, the very slow motion of the moon can cause fading. But these are slow fades, and there's a signal processing technique that can be used to help minimize that effect. So the next slide shows a measurement on the lunar radar cross-section in a cumulative probability distribution. That is to say, the 118 dBSM is roughly the median. Median meaning half the time it's bigger and half the time it's less on this curve. And you can see it varies from when it's rising versus when it's directly overhead transiting. So this tells you that it's not a steady target. Most radar targets are not steady targets. They fluctuate. In a way, it's similar to how a laser beam, whenever you're pointing a laser beam at a diffuse surface, you see laser speckle. That is the interference of a bunch of reflections from different parts of the wall coming back to your eye and interfering in your eye at your photon receptors to form the speckle pattern. So this is, in a sense, the same thing, but it's at RF frequencies. This measurement was done at 425 megahertz, and I mentioned we're working at 144. So another measurement was done here, and this is the distribution. How frequently does it change, or how does it change? It can range from here to here. So if you had a threshold, so you had a threshold, just a hard decision type of detector, and so you set it right here at this amplitude of 10. If it exceeded it, it would detect it. If it doesn't exceed it, it would not detect it. So this would be a false, this would be a non-detection, and this would be a detection. So it's important to know what kind of distribution. The other thing that you learn is if you consider what a Ricean is, a Ricean distribution is different than a Rayleigh distribution. You can see the mathematical curves here, but a Ricean distribution is represented by one strong return with a bunch of smaller returns, maybe on the order of 10 or more lesser returns, significantly lesser returns. A Rayleigh distribution is a collection of about 10 roughly equal scatterers in a target. So a Ricean is preferred. You can see the distribution is more favorable if you set a threshold here. If you integrate this curve, the area under this curve, it's larger than if it's on the other side. So Ricean is actually preferred for a radar. Another consideration I mentioned earlier was what happens to the polarization when it's reflected from the moon. Well, the moon isn't a perfect conductor, and it has mare, you know, the so-called seas on the moon, which are flat, and it has rough areas relating to the craters on the moon. So the specular reflection preserves linear polarization. I mentioned that earlier. That's coming from the lunar mare. And you can see here that the return in time, we're sweeping across the disk of the moon with a short pulse. It's evolving this return here, and they measured the fact that this is specular, preserved linear polarization, and this is diffuse. So the Rayleigh distribution would look different, or the amplitude distribution would look different if you collect all of this together. If you're looking at just this portion, then it's going to look like a steadier target than one that has all of this, because this randomizes the polarization, and that reduces the signal strength to a linearly polarized receiver. Okay, I found measurements that were done at different wavelengths, different frequencies. The lunar reflection coefficient, this was a check to see if the 7% was reasonable. You can see 144 megahertz, or about 2 meters, 200 centimeters is here. And so it's in the range here of about 7%. And you can see the fluctuations here that might have been caused during the measurements of the moon, introducing some variation in the return signal. So now I'm going to talk about the ionosphere and polarization as well as geometric polarization rotations. So if you're an amateur astronomer and you take a photograph of the sky, a long exposure, you can see the stars appear to be rotating. It's actually the Earth rotating, and the stars are moving about in a circle over the North Pole, or the polar axis of the Earth. So the same effect is involved in me transmitting what I think is a vertically polarized signal out towards the moon. If someone on the Earth, if there was no ionosphere, nothing interfering, the polarization would appear to be different depending on where you are on the Earth and what time or where the moon is above you in the sky. So this is another variable. You don't know who you're going to be talking to, so you're not sure what polarization they're going to be receiving. So what I'm leaning towards is introducing the fact that polarization is going to rotate. You're not going to know what it is, and it's essentially a uniformly distributed random variable, and there'll be more about that as we go on. So during my actual first QSOs, which I'm showing here next, this is what the polarization was. And you can see this is the first QSO. You can see the polarization changing from -60 to -61. That's the relative polarization between my horizontally polarized antenna and a horizontally polarized antenna at Romeo X-ray 1 Alpha Sierra in Russia. And there's a different number. Just a few minutes later, there's a different number, and you can see the slope is changing for a receiver that's in Slovenia, Sierra 55 Lima Mike. So again, it's going to change with time, and it's going to change with position. Okay, now we're going to look at the ionosphere specifically, and the ionosphere does a lot worse to the polarization than the geometry of the signal path. The ionosphere is birefringent, which means that if you introduce a wave that's not going to be reflected, it's not going to be reflected. 144 megahertz, 30 megahertz will not be reflected if you're propagating straight up. So we're not propagating straight up, but 144 megahertz makes it through the ionosphere. But a linearly polarized signal is converted to a circularly polarized signal in the ionosphere. That's even true if it's reflecting back down to you at HF, say at 3 megahertz, where you're talking to, say, South America. You're going to have two polarizations present, and they're going to propagate on different paths when it comes back down to the Earth. In this particular case, the circular polarization occurs, and effectively, as you leave the ionosphere, you have a rotated electric field. And what I'm showing here on this side is a right-hand circularly polarized wave, as defined by the IEEE. Physicists define it differently than this, but you can see this is a right-hand screw. If you're familiar with the right-hand rule, you can see the electric field rotating like this. The thumb is the direction of propagation, and the electric field is moving as my fingers are moving. So it's doing that. So what happens? Okay, how much is that? Well, I did some calculations, and this is just an approximation. It's actually an integral through the ionosphere, but if you just look at an example, this is just an example, you can see there's a dependence on frequency here, ranging from where people work, 50 megahertz, 6 meters, out to, actually they go out to X-band now. But if you look at these frequencies, and if you assume that the Earth's magnetic field is 50 microtesla, the average electron density is 10 to the 12 electrons per square meter, and you travel 500 kilometers, then you're going to have 14 and a half rotations. So if you think of your horizontal polarization is going to rotate 14 and a half times. It's going to rotate 3.5 times roughly, but it'll be 14 and a half times 90 degrees. And that's going to be random because it depends on what the Earth's magnetic field is, which varies across the Earth. So it depends on where you're pointing, how you're going through the ionosphere. The electron density changes, and then the path length can change. If you're looking at the moon when it's rising, you're going to have a longer path length through the ionosphere than if you're looking straight up. So how does that change? Well, that's been measured. Dr. Taylor measured it at two frequencies. This is 144 megahertz. This is a round trip from New Jersey to the moon and back to New Jersey. You can see the lunar elevation here is marked in red. Here's sunset, so he's making measurements roughly when the moon is up, and you can see the change in polarization as a function of time. If you look at the maximum slope here, it's 220 degrees per hour, or about 3.9 or so, 3.7 degrees a minute. So this is going to be another variable on top of the geometric polarization rotation. So the total polarization then is random because you don't know who's going to answer your call. And moon and the ionosphere is changing. If there's a solar storm, there's going to be more electrons available. As the sun goes down, it's going to change the electron density. All of these things are varying. And the Faraday rotation, which is the rotation of the electric field vector, is going to change. And the best way to look at this is that the total polarization can be treated as a uniformly distributed random variable, ranging from 0 to 90 degrees. That's what you're interested in. You'd like it to be co-aligned with your your antenna's polarization. So what do I mean by uniformly distributed polarization? Well, the best example, since we're here in Connecticut and there are casinos, is a roulette wheel. Uniformly distributed probability distribution function. There are 36, if you don't count the green colors, 36 sectors. Each of those sectors is 10 degrees. He launches the sphere into this and it winds up on one of these. In a sense, that's what's happening here. You don't know what you're going to get. So how does that transfer into polarization loss in decibels? All right, so the median or the expected loss is 3 dB, which isn't too bad. But you can see here as the polarization, as the probability, as the probability, cumulative probability goes up, the probability loss goes up. So this is basically the cross-pole response of your antenna, which might be 20 dB or 25 dB down from the ordinary gain of your antenna. So this can wreck your communications, or it can prevent you from communicating at all. So a QRP EME station has one polarization and no adaptive polarization signal processing. So this is the hardest thing you can do. You don't know what you're going to get, and that's only part of it as we continue here. So now the question is vertical or horizontal polarization for your antenna. There is a significant difference. All right, so I did easy NEC simulations. That particular program is now free. I'd recommend you getting it. It's a fun program to use. This is my antenna's antenna pattern when it's one wavelength above ground. So it's about 2 meters off the ground. It's a 9-element Yagi, a pretty good Yagi. It's an M squared Yagi, and it's 0 degree elevation. So it's pointing horizontal to the earth. You can see it's essentially very difficult to put RF power down on the ground. You can't do that. On the other hand, the way of looking at this is there's an image response or an image of your antenna. It's as if you put a pencil on a mirror. Here's the mirror, here's the pencil. The pencil is a vertical antenna. It's a quarter wave. On the other side of the mirror, you would see another quarter wave. So that's the equivalent of a half wave antenna. You have what they call ground gain. It's the image of your antenna 2 meters below the earth, assuming that the earth is a good conductor. So easy NEC has different realizations for the earth's conductivity. I took one example. This is what the antenna gain looks like. It's off the ground and it's up roughly at, looks like about 14 degrees or so. So that means it's difficult to see the moon at moonrise with a simple antenna like this. And this is all, I should also mention that was vertical polarization. This is horizontal polarization, and I'll go back one again. Notice that it's only about 15 dB at 9 degrees. Here it's 18.6 dB, and that's because the image antenna is horizontally polarized. You don't necessarily have the same thing with a vertical polarization with a Yagi antenna. So you get what they call ground gain. So knowing this in advance, I planned when I did measurements, when I did my communication examples, to wait for this moon rising. So I would have a relatively shallow angle compared to the ground. So the best antenna to choose for this operation is a Yagi horizontal polarization for angles between 10 and 30 degrees. So the gain is higher than a vertically polarized antenna. But you have to remember, again, the ionosphere is going to change your polarization by the time it gets back to the other guy's receiver. Okay, now I'm going to describe the station I have, the QRP station. We're in Connecticut, and this is where I live. The antenna was placed right here just outside my garage. This is the garage. And I had to shoot the beam between this guy's house and these trees. And you'll see another view of that. The RF main beam hazard zone is 80 feet. And that would be 80 feet if the beam were directly on the ground, and we saw how the beam isn't really on the ground, but 80 feet in front of the antenna. And it's about, I think, 20 feet in the side lobes. This is a residential area, so my neighbors would not appreciate me leaving a 14-foot antenna here up all the time. So I have a tripod that I set up to hold the antenna, and I set it up and get down each time I'm going to use it, and I have to know where the moon is going to be, and this is the window I have, as you'll see in the next chart. This is a 4 pi steradian image from an interesting camera I have. You can see the top of my head here. You can see everything essentially mapped onto a plane. This is my antenna beam width. So I have to shoot for the moon right about here where that laser is. And you can see the beam is large enough and the moon is small enough that it's not too hard to point. Okay, so knowing that, you need to predict where the moon is going to be. There are only a few days in the month where I get these necessary conditions where the moon is in that position. And I'll get to how I predict that, but this is what the window was on January 19th, the first time I operated. You can see the EME window is here. Can't see it at moonrise, and it starts to come up, and here's the moon elevation and azimuth across this period of time. Roughly, this is UTC time, 2030 to 22. So it's about a half an hour window here. And the elevation is changing at about 10 degrees per hour. So once again, elevation determined by the needed ground gain, and azimuth determined by the window limited by my neighborhood. And I pointed the antenna. How do you point the antenna? With a compass and an inclinometer. Because the beam width is so large, you don't have to worry about pointing it that accurately. It's not like a laser where you're pointing a laser. Laser might have a beam width of about a milliradian, and my antenna has a 38-degree beam. So this is what it looks like. This is the window to my garage, and I just ran a cable out here to the antenna, and see no obstructions around here. And this is what the antenna looks like. It's a M², 2 meter, 9-element single sideband. Single sideband is basically for terrestrial communications at 2 meters. They use horizontal polarization. You can change that, but this is the way I worked. So I have a tripod from MFJ, and I made an extension to be able to rotate this in azimuth and elevation. This is just PVC pipe. So the question is, what happens to the VSWR whenever you're this close to the ground? And that's shown here. This is a measurement of the VSWR of that antenna in situ, that is right in position, pointing horizontally. I didn't want to destroy my radio by having a strong reflection from the antenna because the VSWR increased because it was close to the ground. But under these conditions, you can see the VSWR is very low. I think it's about 1.05, something like that, at the frequency of interest. The frequency of interest is roughly 144.1 to 0.2. Now, we all know that if you move the antenna a lot, you can bump it into the side of your garage, and the VSWR can change, but that hasn't been a problem so far. This is a block diagram of the station, the QRP station. And what I've got here, the heart of it is an ICOM IC9100. It's a very nice transceiver. It's no longer available, but it's HF, VHF, UHF. It can run long duty cycles. And it has a nice feature where it can put 12 volts, 12 or 15 volts on the coax out to a preamp. So I have a power supply for it. And then I have a Windows, at that time it was a Windows 10 computer, and I ran JT65B. I'd never run QRA64 or Q65. So it runs this. This software takes into account Doppler shift, position of the moon, and all that. If I had a rotor, it would point the antenna. So this is the preamp. It's from Advanced Radio Research. it has a Vox. In other words, it has a circuit that monitors the RF power here and switches a relay. Depending on whether or not the RF power is available, the power goes on to a power amp, or if it's off, then a signal can come through the low noise amplifier and be presented to the receiver here. Now, this is an unusual configuration. Ideally, this would be up here at the antenna, right at the output of the antenna, to minimize the cable loss and improve the noise figure. Probably would improve the noise figure by about roughly almost a dB if I did that. But if I do that, and there's a problem up here with the VSWR, the power would be reflected back at the input of this LNA. The LNA is rated to 150, no, I think it can take on the order of a couple hundred watts, but I didn't want to chance that. Here I only needed about 12 watts to drive this power amplifier. So it's protected from a return this way. And I haven't seen that yet, so it worked well. Okay, so you can see there are losses in the coax. I used, the longest piece of coax was a 400 max, which has a lower attenuation than RG213. These are such short pieces, I didn't have to use any special coax for that. So how much did this cost? And obviously, before I started buying things, I was doing calculations to see if this would even work. But this is what the cost was in 2018. I've included here also the cost of the antenna software. This is now free. And the antenna analyzer, now I've got a VNA, a nano VNA, which is much better than using this for this particular case. But this is what I had at the time. And I've got a list of all the parts, all the ways down to the cables and the power pole distribution box. If you have a transceiver that works out to VHF, then the price is roughly cut in half. The other expensive components are the VHF linear amplifier, again rated for about 200 watts, and the Yagi antenna. And then there's the, well, meters and things which you may have already anyways. So this is the specification for the system. We're in Pawcatuck, Connecticut, which is right on the Rhode Island border. This is the grid square location and so on and so forth. By the time the 200 watts gets to, or 180 watts or so gets to the antenna, it's about 177 watts. And here I've written it in terms of dBW, decibels referred to a watt. So 200 watts would be 23 dBW. So this is 22.5 dBW. The antenna, I mentioned the antenna gain, including the ground gain. So the total antenna gain is about 16 2/3 dBi. dBi means reference to an isotropic radiator. That is something that propagates into 4 pi steradians. So radar guys take the product of the power and the aperture to measure how powerful the radar is. So using that notation here, it's not necessarily convention of what you do in ham radio, but it's a way of defining a QRP station. This is roughly 40 dBIW. That's equivalent to 10,000 watts radiated into a sphere, 4 pi steradian. Okay, I mentioned these numbers here. JT65B. JT65B is used at 2 meters and at 6 meters. At higher frequencies, use a different format, and the numbers associated with the bandwidths and the tones are a little different. But we're talking about 2 meters. And there are a lot of operators on 2 meters, so I'd encourage people interested in this to operate at 2 meters. So now we're going to enter into a little deeper discussion about the waveform and the signal processing. So what is JT65B? It uses frequency shift keying. So some of you may be familiar with frequency shift keying. That's our phone ringing. I'm going to ignore it. But frequency shift keying, a good example of it was shown in a movie that I'm sure some of you have seen. And here it is. Close Encounters of the Third Kind. Communicating with the mothership here. The information is transmitted in discrete frequencies or tones. The number of tones used in the alphabet determines the frequency content per tone. I'll describe that in a bit. And you can see the engineers here trying to figure out what message is being transmitted using this audio frequency shift key. That's actually a spectrogram. Frequency is vertical and time is horizontal. So now we're going to go into detail on JT65B. There are two message formats. The long message, which is complicated and is the most difficult, has the most information in it, and the short message. So the long message includes this. It has an alphabet of 64 tones or symbols. The English alphabet has 26 letters. It has 64 tones that are used to transmit information. The 65th tone is the synchronization tone. So if you have 64 tones, 2 raised to the 6th power is 64. So that means that each tone can transmit 6 bits of information. So whenever you talk about baud, that's not bits per second. Baud is symbols per second. And you'll see what that is as we go on. The other trick is it uses forward error correction, which is a technique that's basically similar to trying to solve for, say, n unknowns with n equations. Well, in this case, you might have 20 times n equations. And so you get some redundancy. You get, if the equations had noise, if the result was noisy, varied slightly, you could still get the answer by doing the equivalent of a curve fit. So it's taking a bunch of measurements and using them to evaluate the actual message. And so that's done by transmitting excess error correction bits. So within this Reed-Solomon code, there are 63 symbols and 12, 72 message bits, 306 error correction bits, and this has to do with the way the symbols are arranged with the bits that are coming in. So it's 378 bits total and 63 symbols, and those are transmitted across a time of 47.8 seconds. So it's a very slow data rate. If you demand that the data rate be high, you need to transmit more energy. You need more power to basically get the message through. Also, the number of bits, the number of information bits is only 72. So we're only sending 72 bits in 47.8 seconds. So that message is sent once. It's a single code word. The code word is the result of this Reed-Solomon code. It generates a block of data. In addition to that, there's interleaving, and I'll show you that graphically. It's basically scrambling the encoded signal, the encoded bits, so that if you have a fade, it doesn't wipe out a whole group of bits. So it helps protect against fades to some extent. So the symbols, 63 symbols transmitted in roughly 4/10 of a second. And they're interleaved. Half the energy is going into the transmission of the information. The other half of the information is in the sync bits. And there are 63 sync bits and 63 symbol bits. The sync bits are a pseudo-random sequence, like a maximum linear sequence, which means that you can use that to synchronize by matching, if you have the delays, if you have the code as that pseudo-random sequence of bits for the synchronization passes, you can match it up with the appropriate times. In other words, it's like a key going into a lock, where you have the tumblers fitting into each position. Imagine an on-off keyed synchronization like that. And when it fits, that means you're synchronized in time and in frequency, because this is frequency shift keyed. Okay, for receiving, you have to de-interleave and then decode, and then you have to make a decision. for each of the bits that comes through, you have to make a decision. So you can use a hard decision. That's a threshold, like we talked earlier. It's over a certain level, it's a 1. If it isn't, it's a 0. Or you can look and take the collection of data and take the best alternative. And that's done in a couple of ways. If you use the algorithm that he uses here, this algebraic soft decision, gain about 2 dB over hard decision. And then they have something that's really tricky. It's called a deep search decode. All right, so what does that mean? Well, the first time I was operating, I didn't know anything about that. There's a database of about 7,000 hams throughout the world that try to do Earth-Moon Earth communications. You have to put your name into that database for the deep search decode to work. The first time I worked, it said call 3 database missing, call 3 text missing, call 3 text missing. So by talking to other hams, I learned about entering my name and call sign and the equipment list that I have that's appropriate into this database. So that's available, that's on my computer. And so whenever the data comes across, it looks for those solutions that make sense. In other words, if you're transmitting a message with your call sign, it already knows that your call sign's in there. If you're just receiving a signal, somebody's calling out CQ, Kilo Charlie 1, Hotel Tango, Tango, Foxtrot, November 4-1, then that's a harder message or code word to decode. But having an idea of who could be transmitting really makes it a lot better, and you gain another 4 decibels over the soft decision only. So looking at that in a little more detail, the first message is, as I said, it's a call, say, you've already sent out the CQ, and now Romeo X-ray 1 Alpha Sierra, you're answering it, or he's coming back to you. So these are the characters in the message. 28 bits here, 28 bits here, 16 bits. So this is like, it's like FT8. You have 72 information bits. So those 17 characters or bits are encoded in this message block encoder. Then it goes into this Reed-Solomon encoder, and it comes out in one code word. That's 378 bits long, 6 bits per symbol, 63 symbols. That goes into an interleaver, and I'll show you what the interleaver does in the next slide. The input stream is coming here, 1, 2, 3, all the way out to 63. This is an example of a 3x3. It goes into an array, read in by rows, read out by columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's reading out 1, 4, 7, 2, 5, 8, 3, 6, 9. So it scrambles or interleaves the bits. Again, it makes it more robust against fading. Fading where you might take out, instead of taking out 1, 2, 3, you'll just take out these. So it's an easier job for the forward error correction to make up for that. So what does the 64 ARRI alphabet plus sync look like? All right, these are a list of frequencies that represent bit patterns. Each of these is 6 bit patterns. So taking example, symbol number 10, it's binary 10, and it's look like it's 1,329.63 hertz. So that's the tone that sends those 6 bits. This tone spacing is for JT65B is about 6.4 hertz. The duration is about a little more than 1/3 of a second. Again, 6 bits per symbol and so on. 126 tones are transmitted. So the baud rate, the information rate is 2.69 symbols per second, which is very, very low. And the entire bandwidth of this signal, that is, if you were looking at it on a spectrum analyzer, is roughly 350 hertz. So these pulses these tones are coming in, transmitting the information, the 72 information bits plus 308 error correction bits. So what does that sound like? I mentioned how I had heard ham radio operator, Bill Corbin, in Rhode Island back in November 2018. Well, the JT65B software, WSJT-X, records the tones, so you can go back and play them back. So I have that. I have the recording from that first encounter. And it's interesting because there was an airplane where both of our antennas are looking roughly in the direction of the moon, so the beams sort of overlap if you look at the geometry. An aircraft passed in front of his beam. So I received his signal in a terrestrial main lobe to perhaps side lobe or main lobe. No, side lobe to main lobe. And then I received the reflection off the airplane. And so you can you'll be able to hear that and see it in a spectrogram. So that's the full message from Whiskey 3, Charlie, Juliet, Kilo. And that's his message of CQ. It will always be the same. That's what he sends out. You can see here this other set of tones. That's a reflection. You can see the tones are falling off in frequency and they're actually fading out. You can see here this is a cleaner version of this, and you can see the tones here stepping in frequency. Also in here is the synchronization from the maximum linear sequence. Half power in each, the sync, and half the power in the message. Now there are further complications. The moon is not stationary, it's moving in an elliptical orbit, and it appears to have this libration, as you can see here. And that introduces a very small Doppler shift, less than 2 hertz. But remember, we're trying to integrate signals in bandwidths that are very, very narrow. The narrower the bandwidth, the less noise present in your receiver. So Doppler shifts like this can create a problem. It's as if, think of it, you have a Doppler bin, you have a filter, and you have a signal that's moving through the filter. Some of the energy is going to spill out outside of the filter passband, and it's going to reduce the signal to noise ratio. So that has been calculated by Dr. Taylor again, and you can see here at 144 megahertz, the Doppler shifts are very small. This is the limb-to-limb frequency, 4 hertz. And here, this is the 50% median, 0.4 of a hertz. So it's not very much. And most of our signals coming from the center of the moon anyways for this at this frequency. The moon is smoother at 6-meter wavelengths than it is at 10 centimeters. Okay, so what does that do to the performance? So Dr. Taylor has done a number of simulations using additive Gaussian white noise to see how well his system works. And this is the performance for the long message. So far, all that we've been talking about is the long message, the initial messages of greeting, as it were. So you can see the Doppler spread reduces the performance. 1 hertz Doppler shift drops it by about a dB or so. And this shows the percent copy. This shows how well it works. People say, well, JT65 works to minus 24 dB. Well, it actually works down here too. It just doesn't work as frequently. If you keep on transmitting, you may get through. Remember, the ionosphere is changing, the moon is moving, all of these factors may change it, or you might choose, if you can, to transmit at a totally different time, and then you'll have a different ionosphere, perhaps. So that's how the long message works, and it can work down to minus 30 dB under the right conditions, which is an extremely low signal. And what is that? You've heard of milliwatts, microwatts, picowatts, femtowatts, attowatts. Well, there's zeptowatts. These are in the order of a couple hundred zeptowatts in receiving the signal. So it's an extremely low signal in a very narrow bandwidth with very, very low information rates. So the other message that's sent, after you sent the the greeting messages, and you'll see that in the next chart. You have to say, and this is in FT8, you may recognize it. You have to recognize the fact that you've received the signal. You can't tell him necessarily, the conventions are that you don't tell them what your signal strength is, but you transmit RO if you receive the signal, and then the reply is RRR, and then 73, goodbye. So those are all transmitted by single tones, and the format is very different than the longhand message. It's just sync and tone, 16 times. And the tone duration is different. It's 1.5 seconds. And synchronization isn't required. Time synchronization is not required. You're looking at the difference frequency between the sync tone and RRR or 73. And these are the difference frequencies here. So you're detecting these different frequencies. You have 16 times to detect it. I'm not certain if he does an integration, but I've seen the decoder work more than once, which means it's decoded it, and then it sees it again and decodes it again at a different time. You'll see that in the next chart. This is what my first 2-meter EME QSO looked like, communicating to Romeo X-ray 1 Alpha Sierra in Russia. And here, this is important. If you're in the east, you transmit on even minutes. If you're in the west, you transmit on odd minutes. The reason why I heard Bill Corbin in Rhode Island was I transmitted at the wrong time, and I was listening to his transmissions. That doesn't happen here. It also means that you can interfere. Someone in Rhode Island could potentially interfere with me communicating. But there is perhaps a frequency difference and a spatial difference too. But here you can see that the clock, the transmission starts 1 second after UTC minutes. There's a CQ, and these are the 72-bit messages. These are long messages here. So these are all using forward error correction, interleaving, and the lookup table for who does this type of thing. Then finally, you shift to the short message, and you get R0, RRR, 73, 73. So this looks similar to FT8, which I think some of you will be very familiar with. It's just that the tones are different, the number of bits are different, and the transmission times are much longer. As you can see, it's on the order of 46.8 seconds to transmit this message. The same thing happens here, but they're short intervals. Okay, now let's look at the operations. How well does this all work? All right, well, this is what the moon looked like if I could see through the clouds. That particular night, it was a cold night in January. I had to heat up my garage, set up the antenna outside. There wasn't any snow on the ground, fortunately, but I had planned that, I knew where the moon was going to rise that particular night, and it fit the requirements for the EME window that I had. So I'd have antenna gain because of the image of the antenna on the ground, by the ground. So note that the moon is waxing gibbous. That is, it's moving towards a full moon. You do not want to work when the moon is a new moon. That is, whenever it's dark. Whenever it's totally dark, that means that the sun will be in your beam width, and you'll have the noise associated with that. So that was another constraint. Where do you see all of that? Well, there's software you can get called Moonsked, and it was written by this particular ham in England, and you can see he's plotted a number of factors and it calculates things like minimum degradation. And what that means is, well, red here is the sun. You're in the field of view of the sun right here, and so the noise is way up. Over here, the sun is very far away, and you're not looking at any radio sources in our galaxy, so you get minimum RF noise. Some people think that some people say that the temperature of the universe is 3 Kelvin. Well, it's not 3 Kelvin at 2 meters. It's much hotter than that because of the stars that are present. If you don't look at the stars, then it gets cooler. But so you can see here, there's a factor. Right here is where I was working, and it included things like the temperature of the sky, the range, And also this is the effect of the geometric rotation. So this was calculated for a specific example, the one that I'm showing for the Russian ham. So where the software also displays where the moon is, it was over North Africa. This is the station in St. Petersburg, Russia. And here I am in Connecticut. The sun is over here. Light is actually, this is actually night. So it was at night. Wasn't it in the day because the sun is over here. So the software also calculates, as you saw, the azimuth, the elevation is a function of time, and it shows a radio sky noise map. This is a Mercator projection of radio sky noise. You think of the celestial sphere above us. You can assign coordinates, right ascension and declination. What you're shown here is declination and right ascension. It's like a Mercator projection of the Earth, which is a sphere. It's a celestial sphere in this case, projected into a flat Mercator projection. You can see here, here's the path of the sun, this sine wave. And the planets and the moon pretty much follow the ecliptic plane. This is the ecliptic plane. This is the Milky Way galaxy. It's a radio source that's significant, even at, well, this is a roughly 400 megahertz, I think. So it's roughly the same at 144 megahertz. This is where this is my beam. So you can see what I'm encompassing in terms of radio sources, and the moon is right there. So this is how you optimize. If I could have seen the moon here, the background noise would be reduced, although there still is background noise associated with the side lobes touching the ground, touching the Earth. So again, here's the location. As I said, I'm shooting this way. I had 6 QSOs, 5 of them were this way. I did one this way, and it was a very big radio station in Italy. I thought there'd be no problem, but I didn't have the ground gain and barely worked. And there's probably another reason for that that I'll mention as I go on. So, I did something that wasn't quite the best thing to do. I pointed the antenna at the moon, so it was roughly 15 degrees. So it actually reduced the gain from 17.25 to about 16 2/3 dB. I would have done better just to point the antenna horizontal. The beam was up high anyways, but I did this. And this is what the display looks like. And again, it looks a lot like an FT8 display from WSJT-X. So red means that this guy's trying to contact me. So it appears here and it appears here. This is where I work. Yellow is me sending CQs and also replying to this Russian operator. So there's a lot of information here. In this particular view here, you can see here is the delta time. You can see the time here. If you can, it's about 2.2 seconds. It's actually 2.4 second round trip time to the moon at this particular position. So the clocks were off by about 1/10 of a second or so. You can see the RRR and RO decoded here and 73 decoded here. And you can see there are attempts where it didn't work. And these aren't synchronized in time. That's why the time is different than 2.3 seconds. And then over here in the so-called waterfall display or spectrum analyzer waterfall display, you can see the QSOs here. This is where the sync was. It's off from what I mentioned earlier because I'm tuned off a bit. I'm tuned to this guy's frequency. So the sync is showing here. You can actually see the sync pulses because all of that energy is transmitted. Half the energy is transmitted in the sync, and it's one frequency. The long message is spread out here. You can't even see the little blips that represent the tones. On the other hand, you can see RO and 73. These are the Russian signals. That's why it's in red. These are roughly a minute duration, and the gaps here are minutes, and that's when I'm transmitting, so that's not shown. It only shows the Russian long messages and the replies here. So the QSO took place over that period of time, and looking at it, blowing it up a bit, you can see the times here. You can see the signal to noise ratio, which is interesting because I use that to understand what the performance of the system was with my system. This is the signal that he received. No, this is the signal that I received from him. And this is the information. That's his transmission. This is my transmission. I got this number from the next chart. You'll see where I get that. Then these numbers aren't critical. It's a different format. This is the number that I'm going to use to look at the performance. And this is a translation of what these mean, as you've seen earlier. So there's yet another website that has, it's basically like a dating service or a chat or a chat box, I guess, whatever you want to call it. But the point is you can send messages, you can say I'm going to be operating, and you can also exchange messages after you've successfully done a QSO, and you can exchange information. This guy is telling me, he's saying, thanks, minus 24 was the signal to noise ratio. And this was, I think, the angle. I don't think that's I think this is the angle that the polarization was. He has an adaptive polarization. I think that's what that is. I'm not sure. And, this is actually yellow, this is me, and this is my transmission here. So this is my transmission, this is his transmission, this is his transmission here. Okay, so that's where I got the minus 24 right here. And his antenna was listed here. It's 4 times 15 cross pole. So looking on QSO or QSX, you can get a picture of his antenna, his name, his location, and so on and so forth. He has adaptive polarization. He's using both B and H, and there's a software package that takes signals from both antennas and solves for the polarization rotation. It's called MAP65. But you need 2 antennas. You don't do circular polarization. You're actually measuring 2 different measurements, and you're combining them in a vector sense to find out what the polarization is. And then he uses JT65 for the rest of it. Notice his power aperture product is very large. He's got an antenna 4 times 15 elements. That's roughly 23.5 dB compared to my 16 dB or so. And he's probably got about, I say probably, a guy like this would run about a kilowatt or so. So that's 53.5 dBW. That is a QRO station. This is the only kind of station that I can work. And you'll see in more detail why. So here you can see various details. The echo width. This is if it was a round trip travel time. This is information that you can download. These are azimuth and elevation. I used that earlier in a chart that I showed. This is the radar bistatic radar signal, bistatic radar received bistatic radar signal equation. I put that there just to show you that I'm not using a communication format because the moon is a radar target. And you can see here the power aperture product here. Here's another power aperture product. This is, for me, the small antenna and his large transmitter power. This is his large antenna and my small transmitter power. The Doppler, the Doppler loss is in here, but there's also a loss associated with the polarization, which is here. And as we saw, that can be anywhere from 0 to 20, 30 dB, random. So I put that equation into a spreadsheet, and it also includes the noise sources, which include the sky noise. There's a temperature associated with the sky, and noise figures, and a Doppler spread loss. And then I put in an expected loss for the polarization of 3 dB. It turns out that it's larger than that. And here's the Russian station. He's correcting for polarization, so he has a very low loss here. He's got roughly the same spreading loss, and his signal to noise ratio is about minus 23 dB. The signal to noise ratio at his receiver from me This is the signal to noise ratio at my receiver from him. So it's actually larger. And it sort of makes sense because he's got a big transmitter and big antenna. All right, so now we're looking at a comparative signal to noise ratio analysis for 6 QSOs. Okay, so something happened here. This took a campaign that lasted roughly 6 months. Half the time it didn't work. It worked in January and February, but not in March, April, or July. It worked in May. And why? Well, the same setup, except for May, everything was, I was looking directly out at the moon rising at different times of the day. In May, it was in the daytime, actually. But, and that worked. But I believe during from February through July, I think the power to the preamplifier wasn't working. So the noise figure of the receiver was higher. If you look at that and take that into account, there's a correction here. So this is the correction factor. And if you look at the modeled numbers, the losses are all over the place here because the ionosphere is doing this. On the other hand, if you look at 6 different big gun stations, the losses, it's consistent. In other words, I think I can consistently transmit a message to a big gun station, regardless of the polarization issues, because they have adaptive polarization. They have, all of these stations had V and H components in their antennas, and they were antenna arrays. A lot of gain, polarization, adaptation. Therefore, they can receive my signal. I cannot necessarily receive their signal because I have the polarization of the ionosphere changing, the loss factor. So you can see the difference here is very small among all these guys. All right, so how does that translate? Looking at this, this is a very important chart. What's the probability of my station being heard by a station, a QRO station, big gun station, big antenna, across both polarization measured, adaptive polarization? It's very high, 95% or so, up in here. You know, from what I've measured, it's in this region here. If I got a bigger transmitter, it's not going to make a difference. A big, higher power transmitter will not make a difference. It would be, in a sense, a waste of money. It would be better to buy another antenna, and even better to have adaptive polarization. On the other hand, down here, the probability of me hearing a high power station can range from 10%, from what I've seen, actually maybe 0% to 99%, because this is the change in loss caused by the polarization change through the ionosphere. So it's important. The antenna is more important than the transmit power. I can do a lot with 200 watts, but I need a better antenna system. So the proof of the QSOs is in the QSL cards. And these are the QSL cards that I got from European Russia. Just notice here, it's interesting, the RST, the convention is to put O with quotation marks. That means it worked. You'll see that consistently through all of the other QSL cards. That's Slovenia. That's Italy. This is the toughest one for me. And look at the antenna he had. 57.5 dBIW, and I just barely made it. I think 2 things. One was the preamp and no ground gain. The preamp was not working and the ground gain wasn't available. Here we had the preamp not working, but the ground gain was working, and this was okay. You can see the O here again. And then England, there's an O. I think that 26 might mean what his signal to noise ratio measurement was. And then Spain. Now this guy didn't send a QSL card. This is an EQSL card, but he did confirm through logbook of the world. So all of those QSOs count as QSLs. So a summary is shown here. You can see I've done the systems analysis. I used the radar equation. I think that's more appropriate here than a communication equation. I used EasyNet to understand my antenna. And also, you'll see as I talk about potential future work, what I'm doing with the antennas. I modeled the performance. It seems reasonable. And I was able to build a system for less than $4,000, although I can use the parts for other things too. So, and I successfully operated these stations, all big gun stations in 6 different countries, 1 continent. So defining a minimum system, you need a power aperture product of about 40 dBIW. And you can only work big gun stations. I've had people try, ask me to work with their station, and just knowing what they had, there was no chance of it working. I cannot hear my own echo from the moon. The big gun stations can hear an echo of their own signal. There's special echo mode in JT65B. So this is right on the hairy edge. Okay, and it's best to operate at low elevation angles because you have the so-called ground gain. So what could I do to improve things? Well, I could add a twin 9-element horizontally polarized Yagi antenna. You get 3 dB that way, roughly. There's some losses and all in the combining. Or you can use a V and an H polarized antenna. By the way, the separation would be about 10 feet. I've done EasyNet antenna simulations, and you need a boom that's non-conductive, fiberglass. It has to be stiff. Fiberglass is what you need. They cost about $100. It's $100 to ship them. You can mount 2 antennas on those, 10 feet apart. If they're closer than that, eventually the VSWR will go up. And the antenna gain will probably change too, obviously. So you can use a V and an H, and what I would do is orient them this way. So each antenna, they're orthogonal, but they both have a component of ground gain. So I would use those 2 channels, and then I could switch with a remote antenna switch between polarization 1 and polarization 2 to see which one works best. That diversity probably would eliminate a lot of the problems that I've had so far, where I can't hear the other guy. I would transmit on 1 polarization. I wouldn't try switching. Okay, so the final thing would be to do an adaptive polarization receiver. And so you can do that, and what's almost there, and I think others have done it, is you get an SDR Play RSP Duo software-defined radio receiver. It has 2 separate antennas. You can make a receiver that coherently adds the signal from those 2 antennas, and you need the processing beyond that to basically match the polarization of the antenna and polarization rotations caused by the ionosphere. So that would be the ultimate. That's what the big guns are using. They're not necessarily using the SDR receiver. There are other implementations in software and receivers that you can use, but this is something that I think I could potentially do. But first, I'll be adding the twin antenna, just go for 3 dB, and then try V and H, or orthogonal polarizations. So that's pretty much everything that I have to say. Now we can open it up to questions. And if you need to ask a question and you can't get through, you can send me an email message too. So any questions?
The room is open.
Yes?
Okay, I'll start with the first question.
Okay.
In the radar analogy, can you describe in sort of big picture terms what aperture looks like for an antenna? Is that gain mostly?
Yes, yes. There's a mathematical equation that relates antenna gain to antenna aperture, and it's related to the wavelength. And that's one of the reasons why, before I answer completely, I'll just mention on the side is if you have a 2-meter antenna, like I have, a Yagi antenna, 9 elements, it's going to have a certain aperture and a gain of about roughly 14 dB if there's nothing else around it, just in space. It would have roughly 14 and a half dB. If you have an antenna that looks smaller but many more elements at 400 megahertz or 430 megahertz, it may have a higher gain, but its antenna aperture is less because there's a wavelength scaling. And in fact, the antenna aperture, I'm looking at the equation now, so I don't quote it incorrectly. The effective aperture of an antenna is equal to the gain of the antenna times the wavelength squared divided by 4 pi steradians. So that means that even a dipole with 3 dB, roughly 3 dB of gain, isotropic gain, has an antenna aperture, and that aperture increases as you go to longer wavelengths. And it sort of makes sense physically because the antenna physically is getting bigger, even though it's essentially, wire. The length of the wire is getting bigger. The aperture area is getting bigger, believe it or not. So again, the equation is the gain times lambda squared over 4 pi. That's the antenna gain. So you put those numbers in, you have to convert it to dB to get the antenna gain in decibels. So you can write the equation any way you want, but I think most people are ham radio operators and RF guys are familiar with antenna gain. If you're an optical physicist, you think of aperture like a lens. How large is the lens? The bigger the lens, the more light it collects. Lenses have gain. They essentially are antennas.
Thank you.
It looked like Jeff Shapiro raised his hand, and then after that, David and Nicole.
Bill, I got to say it was a great talk before I ask you anything. Very glad to have heard. And good to see you. And good to see you, Roy, also.
Yeah, it's good to be seen, and I'd like to see you.
Anyway, 2 things fairly quickly. The return polarization in the EME, you send out linear. Does it come back linear or is it somewhat elliptical?
It probably comes back elliptical because of the scattering on the moon. It's partially a diffuse scatterer. The specular portion would return a linear polarization, but the diffuse portion probably has a little bit of cross pole. Whether it's circular or not depends on, or elliptical could depend also on the phase delays. So it's scrambled. You lose some, but most of it comes back linear polarized if you're transmitting linear polarization.
So the people who do adaptive polarization are just trying to take the best linear, or are they going to try to do the whole thing and reduce the elliptic?
I think,
perfect.
Well, in principle, I suppose they could. I don't know if they can introduce a time delay, but they can vectorially add the polarizations, the signals from the 2 antennas. Do they adjust time to probably not, but because I think probably not. I think there's still some inefficiency in the adaptive polarization, but I'm not sure of that. I think the big deal is finding out what the principal linear polarization, if you're transmitting linear polarization, what the principal linear polarization is, what it's turned out to be after going through the ionosphere and the geometric rotation also.
One final thing, because I'm not that familiar with noises in this frequency range. Is it primarily sky noise? You use a good LNA, and that's not the dominant source of noise?
Well, if you have the side lobes touching the Earth, then obviously the noise temperature is going to go up. I think, for my calculation, I think it was 300 and some degrees, and it was a combination of, what's out there in space and what's on the ground. That's if you point the antenna at the Earth, then you're going to get the temperature of the Earth. I was operating in January, so it was pretty cold, so that helped a little bit, I suppose. But so the noise is larger than the noise figure associated with the preamp, and also there's loss in the antenna cabling from the antenna to the preamp. So it's not an ideal situation, but I think the gain associated with having the antenna near the ground is better than, probably is a better thing than otherwise. Another thing that could have happened, whenever I pointed the antenna up high, I didn't measure what the VSWR was, because the back of the antenna is approaching the ground. I should do that calculation and see what results. That's the one that had the very big Italian radio station, and I had a very, very difficult time hearing them. And that may have also been the reason why the preamp or the power supply didn't work. Maybe there was a reflection. I don't know.
Okay, well, thank you.
Okay.
Hi, this is David, N1HAC. I was thinking that the big guns would be using circular polarization because the maximum attenuation would be 3 dB, linear to circular. And if you have the circular polarization on the receive side correct, you don't have any attenuation. You have a good receive signal. And that's what we normally use for space work.
Right, yeah. If you reflect off the moon, right hand goes to left hand. If you have a receiver that could receive left hand circular polarization, then that would be ideal. The ionosphere and the position, the geometric effects wouldn't matter. But I think they're doing something more than that. I think they're adding both vectorially. In other words, I don't, if I were to do this, I would not put a phase delay, a length of coaxial cable in there to make it right hand or left hand polarized. I would take both signals and I would combine them mathematically, vectorially, to come up with the correct polarization that's being transmitted. Now, are they transmitting circular? I don't believe so. I think the adaptive polarization work, MAP 65 is done on receivers. I think they transmit primarily linear polarization. Whether it's vertical or horizontal, I don't know. If you go to the higher frequencies, like X band and L band, 1296, there they have waveguides and they use circular polarization. And I think the convention is circular polarization on transmit, but I haven't worked there. Bill Corbin would be able to answer that question. I know he's used an antenna with circular polarization, but it's the microwave antennas, not the VHF or UHF. Doesn't mean you can't do it, but I don't think they're doing that.
Oh, well, no, it's very simple to do that. You put in a quarter wave link in between the two antennas, and you have a relay that switches you between right hand, left hand. And but you also can bring down two signals, put it into a dual channel receiver, and do the phase shift within your SDR. But at 144 megahertz, and coincidentally, I was just talking about this earlier this afternoon in a rocket experiment, the Faraday rotation is significant. So you never know what polarization you're going to get down.
Right, and that's why they use circular polarization. Same thing with talking to the FM satellites. The FM satellites, you can communicate with them with a little handheld, 5-watt handheld, VHF, UHF. But the orientation of the satellite is changing. So it's the rotation caused by the ionosphere as well as the rotation of the satellite. They typically have linear polarized antennas on those little CubeSats.
Yeah, so always if you have the ability to have crossed antennas and run quarter wave phase between them, and turn them into circular polarization. You can also just do it by displacement, so that one antenna is displaced by a quarter wave of the other.
Right. Let me tell you, I've done a simulation because I have the second antenna already, but they're both linearly polarized. I thought, okay, well, maybe I can do one V and one H simply, and then put in a phase delay to do circular polarization, and then combine them, but they're not coincidental. In other words, they're not on the same z-axis, on the axis of propagation of the electromagnetic wave. So I did simulations with that, and it's interesting because you do get circular polarization, but the antenna is pointing a little bit off because of the displacement. So you were talking about a displacement along, say, the z-axis. I'm talking about a displacement across the fiberglass boom of 10 feet. You still get circular polarization with that, at least according to the simulations I ran on EZ NEC.
Yeah, but then you get a interference pattern between the two antennas.
Yeah, there's a squint too. It's also displaced. The peak is displaced.
Yeah, but usually it's done a single boom with crossed
Yeah.
elements.
Right.
But you
So,
can either do it with a phase shift cable, or you can physically displace them so that the
right.
elements are a quarter wave apart.
Right. It means buying another antenna for me. And so what I was looking at, what I can do with what I have now. I do have a power combiner, and I can put in lengths of cable. And in fact, if you remember the old general radio slotted transmission lines, you can buy variable air lines. So you can tune the path length. You put in a fixed length of cable, and then you can trim it with a variable airline. I don't know if you've seen those, but anyone who played around with transmission lines in college might have seen a general radio tap delay line, and you measure the VSWR with a probe along the center conductor. They have them on eBay. So I've
Well,
looked
it's
at,
actually an
I've looked
interesting
at that.
question about what gives you the 3 dB gain. You're going to use probably about the same number of elements, whether you have them crossed or in a linear antenna. Single polarization.
Whenever you said what gives you the 3 dB, is you mean the
Well,
so-called?
to have two antennas,
Oh yeah, right. That would be
you're doubling your number of elements, but
yeah,
to get a 3 dB gain.
right. At best, a 3 dB gain. There's also combining losses.
Yeah,
I have a
but
power combiner, 2-meter power combiner.
David,
very
I
good. Thanks.
think Roy also had raised his hand.
Okay, I think the last person asked the same question I was going to ask, basically. I think we covered that in depth, so I'll be very quick and just say great talk, Bill.
Thanks.
Great seeing you again after all these years, even if it's on Zoom, and also to Jeff and Ron and some other old friends. So this was a great Tuesday evening. Thanks.
Yeah, it was fun. You're welcome. And happy holidays to everybody.
One last question, or one more question. Have you looked through that call text file to see how many other stations there are similar to yours, or how many are at that QRP level compared to, median or whatever?
Yeah. Well, I haven't looked through that table. There are 7,000 entries, and the entries, if they were in a like a spreadsheet, you could put them into a spreadsheet, but the line that has transmit power and antennas usually is sort of under station description. If they were separate categories, or if they could be made into separate categories, you could then sort through them to find out which are QRP and which are the high power. The high power guys have no problem communicating. They just turn on and it works. They can talk to other high power stations easily. They can't necessarily talk to the QRP stations. And so you are a limited asset, as it were. If you have a certain grid square that they need, they're going to look for you. So that's a good thing.
Thank you.
You're welcome.
Did anyone else raise their hand who we missed? Well, Bill, thank you so much. This has been incredibly informative, and we
was
really
fun.
appreciate your time, your effort.
Okay. You're welcome. And I had a great time.